Welcome back, everyone. It's my pleasure to introduce the second speaker of this afternoon, Toby Gee, who will tell us about the Categorical Langlands program.
Great. Thanks very much. It's a pleasure to be here again, giving lectures in this room. So I'm continuing in some sense from Xinwen's lecture yesterday, but it will be kind of largely independent mathematically, at least, although you'll see some similar ideas. So as I said in the abstract, I'm going to just try and sort of talk about the group GL2QP, or maybe PGL2QP, at least today, and maybe at the end of the lecture on Thursday, I might try and also talk a bit about GL2 QP squared, where everything will be conjectural. So my aim is to kind of state some theorem in this case. That would be the kind of goal for today. And then on Thursday, I'll try and give some kind of examples and pictures of what's going on in this case. And then, some conjectural things here. Everything is, I think, pretty much taken from these notes from the IHS summer school last year. So I'm just giving some kind of extracts from that. So if you were there then and you've read the notes, then you don't need to watch this. And if I'm going to try and give some motivation as I go, but for the most part, the motivation was in yesterday's talk and kind of in these notes and so on. So I think I said this in the abstract, but if you find this completely unmotivated and haven't ever looked at those notes, if you look at the introduction, we made quite an effort to write something that was very down to earth and historical and gave some explanation. So you could look at that instead of watching this. Okay, so the goal is to explain the statement of some theorem. So I'm going to try and state the theorem first, and then spend probably a lot of the rest of today's lecture explaining the things in it. So I'm afraid this statement won't make much sense. So this is work in progress with Andrea Dotto and Matthew Emerton. And me. So hopefully there'll be a paper later this year, finally. Okay, so we're going to suppose that P of the prime that's at least 5. There should be an analog of this theorem for 2 and 3, but we haven't attempted to prove that. Let G be the group PGL2 QP. So I'm always going to consider representations of PGL2, so that's the same as representations of GL2 with trivial central character. There's a version of this theorem for any fixed central character, but this is just kind of easier notationally. Let's let O be the ring of integers in a p-adic field E, which is the finite extension of the QP. I'm not sure I'm going to need to use reduction mod P much, but let's write var pi for maximal ideal of O, the maximal ideal in K for the residue field. I think for almost anything I say today, at least, you could just suppose this is ZP and FP, but I'm very carefully trying to stick to the notation in these IHS notes, because otherwise there'll be a disaster at some point. And then I'm going to let X, curly X, over both O be something that I'll define properly in a few minutes. It's the stack of rank 2 étale, not where that goes, Phi-Gallon modules with fixed determinants the fixed determinant is the inverse of the p-adic cyclotomic character. So epsilon for me is the p-adic cyclotomic character. And the fact that I'm talking about things with inverse cyclotomic determinants is related to the fact that this is trivial central character. This was in Xinwen's talk as well yesterday. There's some relationship between central characters and on the representation theory side and determinants on the Gower theory side, which is off by some kind of shift. this could be corrected by using C groups, but I really don't want to do that today. Okay, so that's the setup. Then there is a coherent sheaf L infinity on X, the sheaf of, I'm going to have yet more notation that's not defined, OG modules, so O double brackets G modules, which is flat over some Iwasawa algebra, O double brackets K, again, to be defined, and it's such that the following holds. Okay. Such that the functor sending pi to calling this A of pi, which is defined to be L infinity derived tensor product over OG with pi. This is some functor, and it's an O linear fully faithful exact functor. Yes, as you see, we're calling it A, and it's going from the bounded derived category of finitely presented smooth representations of G, we defined again shortly, to the bounded derived category of coherent sheaves on X. This functor has, it's kind of only mildly derived, it has amplitude -1, 0. So if you feed in an actual representation, you get something, a complex of length at most 2, and extends by taking co-limits to a fully faithful functor on the whole derived category of smooth G reps to in coherent sheaves on X. Okay, so at least I've avoided the trap of failing to state the theorem due to running out of time, but I may fall into the trap of failing to define the things in the theorem. But this is the theorem I want to discuss. I'm not going to really say very much about the proof. Maybe I'll say about a minute's worth at some point, but I want to define everything and then kind of, try and give some pictures and say what this is telling us. That's to be defined in a minute. It's the Iwasawa algebra of the maximal compact subgroup, but yeah, there's lots of things that I haven't defined, obviously, and I will define everything. But notwithstanding that, are there any questions before I start actually saying what this means? Exactly. Yeah, so exact functor means exact in the usual sense of triangulated categories. It preserves exact triangles. And the previous question was what was this O of K, and I'm going to define that very shortly. What are the coefficients of the representations? Again, this is literally going to be the very next ASA, but they are, you should think that these are kind of like Banach space representations or something, but more simply, you should just think that we're mod P or mod some power of P, and then you can take some kind of limits. So there's also a version of this kind of idea that works with like locally analytic representations and so on, and that's also discussed at length in these IHS notes, and I'm not going to say anything about this at all. So this is what we call the Banach version of periodic local Langlands. And yeah, so obviously, hopefully it's somewhat clear that this has some formal relationship, at least with what Jim was telling us yesterday. this X is some replacement for the stack of Vedolin representations that was happening in the L naught P case. So that definition doesn't work well in the p-adic case, and there's going to be this stack of Figaro modules instead. Is the L infinity unique? I guess it's determined by the functor. Yeah, I mean, it's more if you this thing here, this ring, which I'll define in a little bit, is not literally something to which you can. It's not literally a smooth representation, but it's some pro-smooth representation. And you can imagine you can evaluate the functor on it, and then by if you put in pi being this O of G, then you get L infinity out. So yeah. So that's a good question. In some sense, instead of saying there's an L infinity or something, I could have said there's a functor that satisfies some conditions, and then there's just like some kind of Morita equivalence type theorem would tell you that there is some module that you can put in. Yeah. The reason, in some sense, the reason I've stated it this way is that the way that we actually prove the theorem is by kind of constructing this L infinity. So it's not by doing some fancy categorical construction and then saying after the fact that it existed. There's really some construction. Okay, I think I should start giving some definitions. So let's do that. So definitions. I'm going to say what this smooth G is. Oh, perhaps I should just say one more thing, which is this does have to, we'll come back to this. This does have something to do with existing p-adic Langlands for GL2QP. In particular, this does have something to do with the kind of results of Comez and Pascunas. And in fact, we use those as an input to this proof. So I just want to say this is not some new proof of p-adic local Langlands, in case I forget to say that later. Okay, so G is, are the boards high enough at the moment? I guess someone should just shout if they're not. Okay, so G is PGL2 QP. K is PGL2 ZP. And then this smooth G is the abelian category of smooth, to be defined in a moment, representations of G on O modules. These are kind of O linear representations satisfying some topological condition. So what does smooth mean? So maybe I should give my representation a name, like capital V. So we say that, we want to say that for all V in V, V is killed by some power of P. And is also fixed by some compact open subgroup of G. They're fixed by some open subgroup of G. So it's like the usual definition of smooth, but with some additional kind of p-power torsion condition. And this definition works in the kind of similar way to the usual definition of smooth representations and complex representations and so on. And you can consider for any representation, you consider the smooth subspace and that the subspace of smooth vectors, and that is a smooth representation, and so on. Now I can define those group rings. So if H is any compact open subgroup, then in particular example is this maximal compact K. So then USR algebra OH is just the usual thing. You just take the inverse limit of the finite group rings over over the open ideals, open normal ideals. Normal subgroups, sorry, confused myself. So I guess maybe we saw an example of this in, not of this literal thing with this H and G, but like there was an example of this in George's talk this morning where we did this for ZP, maybe ZP cross, I don't remember. Okay, so this is, so this Iwasawa algebra is an Noetherian compact topological ring. Two-sided Noetherian, I think. And then I define this next ring, which we somewhat abusively write O double brackets G. It's not got the same definition. G is not compact. But for any choice of this H, I just define it to be the tensor product of the actual group algebra of G over the group algebra of H with this Iwasawa algebra. Or if you like, that's also the compact induction from H to G of the Iwasawa algebra. Okay, so a priori, this is not, I mean, this is like a module over OG and over this Iwasawa algebra, but it's a kind of straightforward exercise using that these compact open subgroups are commensurable to show that there's kind of an obvious way that you would like to make this into a ring, and you check that this does actually give you a ring structure, and it's independent of the choice of H. Yeah, it's the compact induction. So this is a ring, and it's kind of independent of H in the obvious sense. So yeah, sorry, I should have just written kind of colon equals. Yeah, exactly. This is the definition of OH. This is the definition of OG. Okay, so as you might hope from the fact that I'm talking about it, there's some relationship between kind of, so if I have a representation like V of G, that's the same as giving myself a module over this group ring OG. And then I can ask, is my representation also a module over this kind of completed group ring, which it certainly needn't be. But it turns out that if V is smooth, then it's an easy exercise. Then the OG module structure on V extends uniquely to give an O double brackets G module structure. The converse isn't true. It's not the case that all modules over this are smooth representations. Is this related to Hecker algebras? I mean, in some sense, I guess there is some relationship with Hecker algebras, but not, I think, probably in the sense that's helpful for me to say anything about. Yeah. So in fact, this, if you think about it, it's not so hard to show that the smooth representations of G, so smooth G, is a full subcategory. How do I spell category? Subcategory of the category of modules over this ring. And so, yeah, so we can kind of talk about modules of this. Smooth modules over this are these smooth representations. Okay, so let me see if I want to say any of these things. Okay, so D of I'm going to try and define what am I trying to do here next. I want to define things like this D of smooth G and this D of violently presented bounded smooth G. So let me just define some other categories first. So D of A double brackets G is the derived category of the category of OG modules. That'll be the in category. And then D, I mean, don't worry too much if these definitions don't seem super helpful, but I just want to give them because people have complained before when I didn't give them. People in this room even. So D smooth of OG is the full subcategory where the cohomologies are smooth. Full subcategory. All of whose cohomology groups are smooth. And it's a fact that there's a canonical equivalence between this and just the derived category of smooth G representations. This is more like something I'm going to point out just to kind of put things on a firm footing. And right, so that's some definition, an equivalent definition of this thing here. But now I want to say what this thing is, because this is the kind of thing of primary interest. And I think once I've done that, I've covered the representation theory side of these definitions. Let's see if I can get to that. And there will be plenty of examples of these things, but possibly not today. If you wait till Thursday or you go and look in the notes, you can see actual concrete examples. Yeah, so I'm literally, the smooth modules are exactly the ones that obey that condition. So all the smooth modules, in this sense, each element is p-power torsion. The whole thing needn't be uniformly p-power torsion. I mean, to be honest, for what I'm saying today, and probably for most of my examples, you will lose nothing by just imagining that we're actually just working in characteristic P. So, yeah, I mean, I was saying in general, like there is some characteristic zero thing going on, but it's like an inverse limit of things mod P to the n. So. Sorry? QP over ZP is okay. Yes, that's like something where every element is p-power torsion. So, yeah. Okay, so yeah, so I need to tell you what it means, what this this DBFP thing is. Well, the B is easy. That's the bounded derived category. So I'm looking at complexes of bounded length. But the FP stands for finite presentation. So first of all, I'll tell you what being finitely generated is. So kind of a lemma, the following, we say that sort of a lemma comma definition. We say that a smooth G representation V is finitely generated with FG if equivalently So I'm going to write a few conditions in a row and say that and claim they're equivalent. V is a finitely generated module over the group ring. G, or unsurprisingly, that's equivalent to being a finitely generated module over the completed group ring. And that's also the same as saying, I could put this one as either an exists or an all, but maybe I'll do all H open compact. There exists a smooth representation of H on a literally finite O module. Should have given myself some room to give it a name. Maybe I'll call the module M. And a surjection from the compact induction of M onto V. Okay, and you can kind of imagine how these things relate. The basic idea is that if you're finitely generated, you choose some generators, they're all fixed by open subgroups, you intersect them to get some compact open subgroup, which fixes all the generators, and then that's how you build this module M. Okay, so those are finitely generated things. And then you say that V is finitely presented what we'll call it FP if again equivalently, so one condition is that V is a finitely presented module over this completed group ring, or equivalently, it has a presentation that looks like this. So, or maybe even kind of simpler, V has a presentation. I don't know. Yeah, that's just say, I could just say it has a presentation by a finite length presentation by finitely generated things, but let's make it completely explicit. This is maybe how I'll use it later. Where I'm not going to write it out, but these are as in this description here. Okay, so those are, it turns out, equivalent conditions. Right, yes, I can get rid of that board at the top now. And then the fact that is, as far as I know, not at all obvious is that the category of finitely presented representations is abelian. So it's an abelian subcategory of the category of smooth representations. And so this is not, at least not known to be a general fact. I mean, I hope it is a general fact, but it's only known, well, it's known for PGL2. QP is actually known for PGL2 of any extension of QP. It's known for GL1, and it's not known other than that. So kind of, it's a proposition proved by Jack Shotton. I guess I'm just going to make up some notation. Smooth G, I'm not going to look at the, hopefully this is obvious definition. So this is the finitely presented smooth G representations. This is an abelian category. So the analogous thing is true for GL1. So it's also true for kind of GL1 of F and PGL2 F over QP arbitrary. So in this case, the corresponding completed group ring is actually Noetherian, and then it's easy. And here, Schotten shows that the group ring is coherent, which is enough to give this. Then you kind of expect that this is true for general reductive groups, but it's then going to be harder because it's known that beyond the case of rank 1 groups, these kind of completed group rings are not coherent. So this is true. It's not just true for general kind of ring theoretic things, but it must use actual smoothness. Okay. Well, I think the GL2 case was not in the literature before, but yes, it is also true for GL2 as well. This is not dealt with in this paper, I think, exactly, but we can talk about this afterwards. But yes, basically the same argument proves GL2. But this is one of these arguments using kind of amalgams on the tree and so on, and it's very much a kind of GL2 argument. Okay, and so I can now just define this category, if I can remember what it's called. So this is exactly the things, kind of bounded complexes with finitely presented cohomology. And so in fact, because p is greater than or equal to 5, and this is also a non-trivial argument, but it kind of maybe you can see why more of this should be true. The ind category of this is the derived category of smooth G representations. I mean, I'm writing equals somewhat abusively, and BFB PD is just the compact objects in G. Again, if you don't know anything about this, then just don't worry about it. But these are the facts that explain the passage between the finitely presented version of the theorem, and I said it extended by taking co-limits to a more general one. So this is false. These statements are not correct if P is 2 or 3, because the pro-P Iwahori subgroup has P torsion, but this is kind of a side point. Probably have to be a bit careful, like probably admitting that this is true. I think it probably should be possible to prove that when the pro-P Iwahori subgroup has no P torsion, then this is true, but I didn't think carefully about it. At least the argument that we have is not completely formal. It kind of uses a bunch of things, so I shouldn't claim exactly what it would need. But I mean, I believe this kind of thing should be true. No, I'm not using. Let me not repeat the question because it's not so relevant. Okay, so that's the end of my rep theory summary. So hopefully I defined all the things on the representation theory side of that theorem. And as I say, I've given you 0 examples, but the examples will come. Are there any questions before I do the kind of spectral side, the phi gamma module side? Compactificate, do you mean this, the compact objects? Sorry, yeah, so terrible handwriting. Probably I'm clearly not writing big enough. I think my handwriting is shrunk. So yeah, these are the compact objects in this category. Sorry, I'll try and write a little larger. Okay, maybe I should move to a new board to start talking about phi gamma modules. Maybe I'm not as tall as I think I am. Okay. Okay, so So I'm going to briefly kind of define what phi gamma modules are and what these stacks of phi gamma modules are. And I'm completely just going to stick to the case of QP. So kind of everything I'm saying for this section has analogs which are much more general. In particular, I could replace QP with any finite extension, but I don't want to do that. Okay, so let's let A be a finitely generated O mod pi to the A algebra for some A greater than equal to 1. So just some P power portion finitely generated algebra. And then I'm going to give, so what I'm going to try and define is a phi gamma module with coefficients in this ring A. And that's going to be some kind of module over a Laurent series ring in one variable over this A. And it has, this thing has actions of phi and of the group gamma, which is just ZP cross. And these are A linear actions, and the Frobenius phi takes T to 1 plus T to the P minus 1. And the action of gamma is basically the same formula. For any A in ZP cross, I define A of T to be 1 plus T the A minus 1, where again you can, this definition is obvious, and this one, because I'm looking at periodic numbers, you have to kind of check the binomial expansion makes sense or something, but it does. And yeah, so these are extended A linearly. And then the definition of a phi gamma module is the following. So a rank D will become 2 shortly, but it costs us nothing to a general definition. Et al.'s phi gamma module with A coefficients. It's a rank D projective module over this Laurent series ring. So a rank D projective A double brackets T module with commuting continuous actions of phi and gamma. I should say semi-linear actions of phi and gamma. So the continuous is just there's some continuity with respect to the kind of t-adic topology. And the semi-linear just means the usual kind of thing, that if I do sort of phi of lambda m is phi of lambda phi of m, this kind of thing, where abusively you tend to write phi both for the action on the coefficient ring and on the module. Okay, similarly for gamma, and these have to commute. That's almost the definition. That would be this definition without the word et al. And for the word et al, I want phi to be an isomorphism, but I can't quite say that because, well, because it's not, because it's a semi-linear map. So kind of the linearized version, which is like a map. Every time I do this, I fail to give my module a name, so I can't write a formula. So let's call the module M, phi upper star M. The kind of induced map to M is linear. So this is the Frobenius pullback, and then you get an induced linear map, and then you can ask that it's actually an isomorphism. And that's what it means to be et al. What is pi? Phi. Yeah, so phi was on here was just this Frobenius map. And then I'm just giving it an action of phi and an action of gamma. So phi is like is a semi-linear endomorphism of the module. And similarly, there's a semi-linear action of gamma, they commute. Does that make sense? Yes. Sorry, can I explain? Yeah, they both have some continuity condition, which is that the kind of action has some t-adic continuity. Right, the module M acquires a natural topology from being a finite projective module over this. Yeah. These things, I mean, implicitly, probably it's better to define everything in terms of some kind of integral structure inside if you want to think about the topologies, but yeah. On the other hand, the mean is kind of the one you might expect, where if things are close together, if you have some element of gamma, which is very close to the element 1, then it should be acting, when you write down a formula, there should be a big power of t in how it acts, or in how gamma minus 1 acts. Okay. Okay, so these phi-gamma modules were introduced not quite in this definition, but when the coefficient is, for example, when the coefficients A are just FP or something, these were introduced by Fontaine, because in that case, they classify Gauss representations. So let me just tell you that, and that's the motivation for this. And that's why considering stacks of these phi-gamma modules is some sensible analog of what Shimon was telling us yesterday. Stacks of Wedelin representations are also like stacks of Gauss representations. These are like stacks of Gauss representations, but they're in different worlds, the kind of L naught P and L equals P worlds. So Fontaine showed, among other things, that if A literally is just this kind of finite quotient, and again, this could just be Z mod P to the A, if you like. That would be a very sensible thing to think about. Then these phi-gamma modules et al. Rank D are naturally in bijection with free rank D A modules with a continuous action of the Gauss group of QP. So GQP is my notation for the absolute Gauss group of QP. And by taking limits and so on, you can extend this equivalence to a slightly larger class of rings, so like it holds over ZP or QP and so on, complete local Noetherian rings with finite residue field, that kind of thing. But this equivalence crucially does not hold for A in the generality I've defined it there, as I'll show you in a minute. And yeah, this is not some kind of mysterious bijection. This is one of these very natural kind of things where you take your phi-gamma module and you extend scalars. You can go up to the bit vectors of C flat and take Frobenius invariants, and that gives you the Gauss representation. And kind of conversely, there's also an explicit recipe. But we're not going to use that. So let me instead finally give you an example of something, which is the kind of rank 1 case where A equals FP. So let's take A equals FP and D equals 1. So let's see, in this is a case where Fontaine's equivalence holds. So first of all, probably more familiar are these representations here. So the kind of characters, these are just characters of Gauss group of QP. So GQP to FP cross, or I could even, I could do FP bar cross if I wanted, are kind of all of the form. What's my notation going to be? Kind of lambda times epsilon bar the I. So epsilon, if you remember, was my mod P 6 atomic character. So where lambda is unramified, with lambda of Rob P equals an element lambda in FP cross. This is probably a fatal experiment. I feel like if I choose different letters for the character and this. They both become lambda at some point, so I'm trying to make them both lambda now, but hopefully this makes sense. So there's some unramified part, just given by where Frobenius goes, and then there's some power of the sixth atomic character, and in characteristic P, the P minus first power of the sixth atomic character is trivial, so this is, well, maybe I'm just going to literally crudely index it by integers. But if we find mod P minus 1. So these are all of the characters. This is, if you like, some exercise with class field theory, although it's a little bit close to being equivalent to the statement of local class field theory for QP, I guess. But if you believe Fontaine's theorem, which you should, then you should similarly be able to classify the rank 1 Étale-Figel modules. And indeed you can. So this character corresponds to the rank 1 Étale-Figel module. So a rank 1 module over, in this case, I've got coefficients in FP. So this is actually just a field. So I'm looking at a vector space. So let's write E for a generator. And I can choose my generator so that phi of E is lambda E. And the A in ZP cross, A of E, I guess, is just A to the, I don't know what I called it. Was it I? A to the I, E. Okay, so you can choose a basis so that this holds. And it's a slightly harder exercise than you might imagine if you've never seen this before, to check that this is also a list of all the rank 1 things up to isomorphism. How do I regard A is in ZP cross? Oh yeah, so I'm reducing mod P to get into FP cross, and then it's in here. So yeah, maybe I'd be better off writing a bar here. Thanks. There's an analogous version if I had like ZP coefficients where I didn't have a bar here, but yeah, thanks. Okay, so that's an example. But now you can kind of see that this is this equivalence of Fontaine's really doesn't hold more generally, because a very easy exercise is to check that if I replace FP with any finite generated FP algebra A, capital A, this definition makes sense as long as lambda is a unit. So if A is, let me write this, any finitely generated FP algebra, and kind of lambda is in A cross the units, you can define an Étale-Figel module just by these formulas. But typically, I mean, you can also imagine you know what the Gauss representation is, because I've told you kind of what it looks like. And so you just have to ask, is there an unramified character taking Frobenius to my lambda now in this more general ring? And the answer is no, because we're not talking about the Weil group, but the Gauss group. So to make an unramified character, I have to be able to raise this thing to arbitrary p-adic powers, or kind of powers in Z hat even. And I certainly can't do that if I just take a random thing. So for example, if I just take kind of almost like a sort of universal example, if sort of lambda is the element X in GM, as it were, so FP XX inverse, there is no corresponding Gauss representation. But on the other hand, this does give you some kind of Étale-Figaro module over this GM base. And so if you like, you can think about that as being a family of Figaro modules by specializing X to be anything in FP bar or something. And it's kind of some very nice family. But while whenever you specialize at a point, you get a Gao representation, you get an unramified character, there isn't a Gao representation over the whole thing. So the kind of moral, which holds very generally, is that families of Figaro modules are much bigger than families of Gao representations. And they're kind of nicer to work with in many ways. Okay, so that brings me to families of Figaro modules, which is kind of the last thing I need to define to have stated the theorem. So let me just make the definition. So definition, X over O is the stack. I'm being slightly informal. I'll say what I mean precisely in a second. For any A as above, I'm going to write in a moment. So X of A is the groupoid of pairs D theta, where D is a rank 2 Étale Figaro module with A coefficients. And theta is the data. I wanted my things to have fixed determinant, and in this kind of Stacky world, I'd better record that data. So there's some obvious linear algebra you can do with Figaro modules. So I can take the wedge squared to get a rank 1 thing, and I want that to be isomorphic to the inverse cyclotomic character, where I have to explain what this means as well. This is a character of the Galois group valued in ZP cross. I can just base change, that corresponds to a Figaro module by Fontaine's theorem, and I can just base change to A to any coefficient ring to get a rank 1 Figaro module that I abusively denote by this. So this is rank 2 Figaro modules with fixed determinant equal to the inverse cyclotomic character. Okay, so this is all a bit abusive because here A was, at least implicitly, but I'm telling you now, A was as above, so it was just finitely generated O algebras. You might want to care about values on bigger algebras, but this stack is kind of by definition, if you like, or you can define it in a more complicated way. It's a limit preserving thing, so it's determined by its values on these. And in fact, what I'm about to tell you is it's a very reasonable geometric object. I can just turn the page, so I don't have to go back. So here's the theorem about these things. So this is a slight variant on the theorems that Matt and I proved kind of about rank D things. We didn't prove anything about fixed determinants, but you can prove it in the same way. So X is a Noetherian formal algebraic stack. And there exist, maybe for reasons of time, let me not define them, but kind of crystalline and kind of semi-stable I'm not sure if I'm going to need them at some point next lecture, so I want to just mention them, kind of X, Chris, Lambda, and various generalizations of this, whose kind of let me sort of say VP points, or maybe, sorry, O, but more generally, extensions of O points correspond to kind of crystalline, etc. Representations of Hodge-Tate weights. Lambda. I'm basically skipping over this part because, as I say, I may well not need it, but say that. We proved some things about those stacks, which I will come back to in the unlikely event that I need it. But let me just go back to my whole stack. So this thing is very definitely a formal kind of object, but the underlying reduced stack, the kind of like the largest reduced thing contained in here, this is necessarily defined over the residue field, and it's a finite type stack over, I think I was calling the residue field of OK, like, or just you could just say it's just over FP, and it's equidimensional of dimension equal to 1. I'll say a lot more about this stack, this reduced stack, underlying reduced stack next time, and draw some pictures and so on. Maybe I also want to say its irreducible components have a natural labeling by Serre weights. Again, this will be explained next time. And maybe fourthly and finally, X itself. I'm going to put this one kind of in quotes because I'm not sure that everything here has a definition in literature, but it's LCI and equidimensional of dimension 4. So the reason I'm putting this in quotes is I think LCI formal algebraic stacks and their dimensions maybe are not covered in the literature, but what I really mean here is, I mean, this is something going to be true, and this statement will be equivalent to some statement about the versal rings, which are Galois deformation rings, and then these kinds of statements, where in this case, where I'm assuming that P is at least 5 and I'm doing GL2QP, this is pretty well known that these things of this form, but in general, this bit paper, Berkeley, Younger, Pascunas proves kind of corresponding results for general GLD. So the difference between the underlying reduced is 1-dimensional, the whole thing is 4-dimensional. One of the directions is the p-adic direction, going from the special fiber to ZP, and there's also 2 completely kind of formal directions as well. And again, maybe we'll see something about those next time. So anyway, next time there'll be examples, maybe some pictures and so on, but I think I will stop because I think I've finished stating the theorem and run out of time.
All right, thank you very much. Are there any questions, further questions? Yes.
What does it mean to be equidimensional of dimension 1? I just mean that every irreducible component is 1-dimensional. I mean, like, I'm thinking like the affine line over a field would be one-dimensional, for example. I mean, this is not the affine line because there's some stacky dimension, but we'll see what this thing kind of looks like. It looks something like more like A2 minus the origin mod of GM, that kind of thing. That's what it looks like. But I'll do this on Thursday.
That's a question.
Yeah.
Oh, no.
No?
Sorry.
Someone? Yes, okay. The question is, what is the substack corresponding to actual representations of the Gal groups? That's an excellent question. There is a largest substack over which there is an actual Gal representation. And basically the way you get it is, so in the GL1 case, it's literally, I had that kind of, this thing with maybe ignoring the stackiness, it literally that kind of GM family I wrote down is the kind of the universal family. And there, the way I get the kind of Galois stack is I formally complete at every closed point, every FB bar point, and take the disjoint union of all those formal completions. So in general, for this GL2 thing, I have to do something a little more complicated because there are genuine families, algebraic families, but the only families you have are families of extensions of characters, sort of chi1 star 0 chi2, where these two characters are fixed and I allow the extension class to vary usually into the one-dimensional space. So each family like this gives me some actual closed point of the underlying reduced, and I take the disjoint union of the formal completions at those points. And that's what this thing looks like. So it's some kind of like, I don't know, fractal is not quite the right word, Cantor set-like thing where I take all the closed points, take the formal completions at those points, and take the disjoint union of them. And that's the underlying stack where you have Galois representations. Yeah. That's epsilon inverse. So epsilon is the p-adic cyclotomic character. Yeah, or this is abusive. It's the phi gamma module that corresponds with it. Corresponds to it, base changed from ZP to this ring, whatever my ring of coefficients is, A. Sorry, so this is literally a character of the Galois group, like a character GQP for ZP cross. And so by Fontaine's theorem, that corresponds to a phi gamma module with ZP coefficients. And then I just have to sort of tensor over ZP like this. This is actually the wrong thing. This should be some p-adic completion, but basically I'm just taking that thing, base changing it to A, and then, yeah. You're welcome. Yeah. Why is it a tal? I'm blanking on the best answer to this. I mean, this goes back to like cats or something, but why are these called a tal? Yes, yeah, okay, the characteristic polynomial of the matrix defining phi is a tal. Thanks. But no doubt people in the back row are all thinking of better answers they would have given, but no?
Yeah.
Like the points in the underlying reduced or the, I mean, yeah, so if I take a,
so the question was,
yeah, so I'm sorry.
Sorry, that might.
Yeah. If I take a point in the underlying reduced, like that's literally a mod p Galois representation, perhaps then I could ask what its stabilizer is, and then like typically it's like I have to be a bit careful about non-closed points and how they vary. But if I just take semi-simple representations, for example, then the stabilizers are just the stabilizers of the groups. So here I guess I've got fixed determinants. I think probably the stabilizer in if I have a direct sum of characters is some GM or something, and if I have like the scalar representation, the trivial representation, then it's an SL2, this kind of thing. There's a relationship between phi gamma modules and the kind of Langlands parameters. So as I think both the things we saw, like the Vadeline representation type things, and these are just kind of versions of Galois representations. in some sense. And so Langlands parameters in some sense are just, for the purposes of these kind of the talks we're giving, you can think of those as being Gauss representations. And so that's the kind of connection. I think it's probably fair to say that both the stacks this stack that I gave and the stack that Jim defined are kind of motivated by you have like a notion of a Gauss representation or a Langlands parameter, and you want to work out what it means in families, and you think about some kind of possible definitions, and you kind of choose the one that works, that gives you the right kind of geometry and so on. There's certainly, I should say, there's like various other equivalent categories, obviously equivalent ways of writing the same data, in terms of modules over various other rings and so on, but they all have a similar flavor, and the point is they all give the right behavior. They give these things which are genuinely these nice algebraic stacks with sort of equidimensional and right number of components and so on. And the points, just the literal points, FP bar points, are what you wanted.